Hi guys, welcome back. We're going to take a look at connecting the equation of the rational function to its graph. And really what we're looking at today is going to be a focus on the asymptotic behavior of the graphs. And what we really mean by that, especially in this set of notes, is we're going to be focusing on the end behavior of the graphs. And not so much as the end behavior in terms of does it go to infinity or negative infinity or to a horizontal asymptote, but we really want to look at more in detail about how do we get horizontal asymptotes, when we might have slant asymptotes, or other asymptotes, kind of taking a look at it. First thing we're going to do though is we're going to do a quick review of what you learned last week, just to make sure that we're okay on that. So I have a function here. That function is g of x. They went ahead and factored it for you because we're going to do a real quick review on this. So I am going to write Fred, the simplified version here for myself to use, okay, with my exception where x does not equal -1. All right, so the first thing we're going to look at, we're looking at the non-canceling factors in the denominator. So what factor is left in the denominator after I've canceled it out, which would be x plus 2, set it equal to 0, so x equal to -2, which I am going to remind you, I will just go ahead and come straight down here. When the equation, scroll down, when the equation has a factor in the denominator that does not cancel out, then the graph must have a vertical asymptote. And when you're looking at this, if I were to classify the type of discontinuity that was there, this would be an infinite discontinuity on the graph. So the graph itself is showing a vertical asymptote. The type of discontinuity would be an infinite discontinuity. All right, let's take a look at our non-canceling factors in the numerator that we're going to look at. So the non-canceling factor in the numerator is going to be the -2x plus 3. We're going to set that equal to 0. Okay. So that's going to give me 3 equals 2x, or x equals 3 halves. And so let's remind ourselves what that does for us in the graph. So that, we'll scroll down. When the equation has a factor in the numerator that does not cancel out, then the graph has a 0 or x-intercept at the x value that makes that factor equal to 0, okay, provided that it does. All right, let's come back up here to the top. Now we're looking at canceling factors in the numerator and denominator, the ones that we took out, which would be this x plus 1. So I'm going to highlight that in pink for you. So that one would be the x plus 1 equals 0, or x equal to -1. And then we're going to remind you, coming down at the bottom, that when the equation has a factor in the numerator and denominator that does cancel out, then the graph has a hole on the graph at the x value that makes that factor equal to 0. This is called a point discontinuity. And then I'm going to add one more thing to this kind of before we leave. I'm going to remind you here at the top that usually once we get that the x value for the whole location, once we know that's what we're looking at, we do want to take the reduced version and we want to plug -1 in, and we want to calculate what we get. What is that? 5 over 3? No. -1 plus 2 is 1. So it ends up being exactly 5. So we can see that the coordinates here are going to be -1, 5 are the coordinates of the whole. So we do want to use the reduced version in order to get that. So I'm just going to say location, ask Fred, and you guys will know what I'm talking about for that. Sorry, I keep forgetting I gotta scroll down. So location, ask Fred. All right, and then our last thing in terms of our review that we're going to take a look at is that we're looking at the quotient of the constant terms. Let's see, what color do I have left to use? I haven't used green. Let's use green. So if I take the constant terms in the numerator and in the denominator, highlighted them in green for you, that we would have 3 over 2, which there's no simplifying if you want to. We can write it as 1.5. And remember that that is telling us what our y-intercept is, 0, 1.5. We can check that on the graph right here. We can see that we have the point, 0, 1.5 here. And then down here, when the equation is in standard form, completely multiplied out, the ratio of constants is the point 0c, where c is the quotient of the constant terms. Trying to think what word I wanted to put there. The hold that thought for a second. It's been a long day. Forgot what I wanted to write there. We're finding it by the ratio of the constants, but it's the y-intercept. And that's the point 0c, and c is the quotient or ratio of the constant terms. So what goes into this little spot right there is that it is the y-intercept. All right, so that's a good review of that. So now we're going to come down and we're going to first start talking about horizontal asymptotes and when they exist. All right, so what the first thing we're going to do is we're going to take a look at the two graphs that we have below. Clearly, a couple things going on here. They went ahead and they already gave you the graph. I'm going to go ahead and simplify because that's always something important to do as you're analyzing these. This would be x minus 3, x plus 2. So we do have some cancellation. I also know that I have cancellation because I do have a hole at that location. So that location, 1 over x plus 2, where x does not equal 3. If I plug in my 3 into the reduced version, Fred, I would get 1/6, and that would be the location of that hole. We have a non-removable factor of x plus 2. Notice that we have a vertical asymptote, x equal to -2. Just kind of recapping where we were from before. Notice that there is no factor in the numerator to set equal to 0, so there is no x-intercept on this one. And then if we take our ratio of constant terms, -3 over -6 is 1/2, and we have 0, 1/2 on our graph. So just kind of putting that all out there. So really kind of looking at this, we can very clearly find the vertical asymptote, but then the question is, what about the horizontal asymptote? And I'm just going to do this in green so we can take a look at it. Now, a couple of things that you want to notice on this. Compare your degree of the numerator to the degree of the denominator for these two functions above. And so when you're looking at it, you're going to see that this degree is 1 or 2. The degree up here, it's not written, is going to be 1. Same thing over here. We're going to have a degree of 2, and we're going to have a degree of 1. So a couple of things you might notice. The first one, what I was really going for is that the degree, actually write in pen here, the degree of the denominator is larger than the degree of the numerator. And so that ends up, and it has a horizontal asymptote. And notice that in both cases, our horizontal asymptote is at y equal to 0. And that actually is true. I will leave it to you to verify this. And notice, I know that in this case, you're like, well, the degree of the denominator is exactly 1 more. I might throw out here one for you guys to go ahead and graph on your own through Desmos. If I had x plus 2 and I did something like x cubed plus 5x squared plus 6x minus 1. Whether that factors or not doesn't really matter to me. We're just looking at whether or not it has a horizontal asymptote. This would also have a horizontal asymptote of y equal to 0. And so, and you can play around with this in Desmos and do a bunch of different things. But really, we talked about this in Algebra 2, that when the degree of the denominator is larger than the degree of the numerator, then it goes to 0. And part of this has to do with the idea that what we're really doing here is, we'll talk about the right-hand limit. The limit as x goes to infinity of this function f of x, I'm going to do the numerator divided by the denominator. And so what we're looking at in those terms is thinking about what happens as x goes to infinity. Now, I like to call this survival of the fastest whenever I'm talking about this, especially in my calculus classes, is this idea that because the degree is larger on the bottom, that what's going to happen is the bottom is going to go to infinity a lot faster than what the numerator is going to go to. A lot of times when we take a look at a problem like this, we consider this in terms of simply saying, hey, who's the winner in the numerator? In the numerator of, say, it doesn't really matter which one we're looking at, they both have the same winner in the numerator. The winner in the numerator is going to be x. You can actually ignore the plus 2 when you're doing this idea of trying to figure out who wins the race or where is the end of the graph going, that the plus 2 is kind of negligible. So the x controls the numerator the most. And the same idea goes for the bottom. The x squared is what's controlling the bottom the most as we are looking at it. So we really could consider this when we are doing this end behavior of really looking at what happens, because I'm just going to cancel out the x's. And this only works when you're doing end behavior. This is not something valid for algebra of simplifying, but for end behavior, what turns out is that the dominant function, which in power functions is going to be the one with a higher degree, dominates, and that's the one that's going to control the ends of the graph. And so once we get that that's going to control the ends of the graph, and I simplify, I'm basically saying what's happening as x goes to infinity. And you know that 1 divided by a really big number is going to be basically 0. And so that kind of shows us the right end behavior. And a very similar argument works for the left end behavior as well for polynomials. And so they're very similar to each other. So they're both approaching 0. So pretty much every time the degree of the denominator is larger than the degree of the numerator, you will have a horizontal asymptote at y equal to 0. All right, so I'm just going to finish out this video, this first video for today's lesson. We're going to scroll down to the bottom of page 3, and let's go ahead and put down the first rule of the 3 rules to determine whether or not you have horizontal asymptotes. All right, so the first one is the degree of the denominator is larger than the degree of the numerator, which is going to imply the function f of x has a horizontal asymptote at y equal to 0, that horizontal line. And so that would be that's the easiest case that we have. All right, so now we're going to come back in and I'm going to let you guys ponder the next 2. And we're going to throw up some questions, see if you can see some patterns on that. So on this one right here, you have 2 functions together. Go ahead and talk about what the relationship is of the numerator to the denominator's degree, and then tell me what you notice about whether or not it has a horizontal asymptote or what you see. And then come down here and we're going to talk about this one. What do you notice about the degree of the numerator compared to the denominator? And talk about, this one might be a little harder, but go ahead and think about, try to remember from Algebra 2 what you would have gotten for that, and we'll come back in part 2 of this video to discuss these in more detail.